Let's summarize what we've got to so far. Any integral of this form, where we have a functional of a large number of functions and their derivatives, is minimized or maximized if and only if the functions themselves satisfy the Euler-Lagrange equations. Physically, we discovered that there's this thing called the action, which is the time integral of the Lagrangian, and in physical processes, this action is minimized, so things take the least action. We derived this from Newton's laws, assuming that the forces acting on the particles were derivable from some potential u. And we found that we could construct the Lagrangian from t minus u. Turns out that is a limited case, in fact, and we can deal with a wider range of Lagrangians that include non-conservative or even velocity-dependent forces, provided we can write them in this form. Then in fact the principle of least action follows, because we still get the same Euler-Lagrange equation from there. So this is very useful to know if you're dealing with complicated situations where you have friction and that sort of thing. At the very fundamental level, all of those things are actually approximations to lots of microscopic processes. And at the microscopic level, in fact, we always have a very well-defined Lagrangian. When we start talking about things a bit more broad than simple point masses, then the Lagrangian takes a slightly different form, but we can always find one and everything behaves beautifully according to the principle of least action. Now, I promised that using the principle of least action was a more efficient calculational technique as well as just a more fundamental principle. And in order to do that, we have to do a lot of examples. So in today's lecture, we're basically going to be going through examples so that you can get a feel for the power of this technique. And the very first thing I want you to try, and in all of these examples, I want you to try the example cold before you watch the video of how it's done. In the very first example I want you to try, I want you to simply derive Newton's laws of motion. In other words, I want you to assume that the principle of least action holds and derive Newton's law. So go that way, and you'll find it a lot easier than it was coming backwards. The general method for doing this falls simply into 3 steps. 1, choose your coordinates. 2, find the Lagrangian in your coordinates. And 3, use the Euler-Lagrange equation. Alright, so go ahead and try and derive Newton's laws of motion.